Welcome to this conversation on simulation in healthcare analytics. A little bit of terminology just to make sure that we're clear, because we've talked in general about healthcare system modeling initially in the video before that. That is creating an explicit, simplified representation of how health systems work. But now we're moving on to a more specific tactic, which is simulation. That's running that representation forward in virtual time, often many times over, to see the range of possible behaviors under different assumptions. So that's what we're transitioning to. It's the actually using this. So we built that model for the purpose of simulation. Simulation is how we press play on that model. And the important nuance here is that the model is just our description of the overall system. This simulation is that execution of that model to create trajectories, summaries, information. So when you hear those terms used interchangeably, someone just might not be being precise. So you may also hear them put together like this, a simulation model. That's just shorthand for a model whose primary mode of analysis is simulation. So just some terminology so you don't get tripped up if you're looking up content other places, and just to get you a little bit more clear there. A little bit of review from our last video. Remember that we're trying to move towards this more useful definition of advanced analytics in healthcare, and I think simulation is part of getting us there. I believe a more useful definition of when a health system is actually producing advanced analytics is when they can repeatably translate raw data into trusted insights and operational change. We recall, in a complex adaptive system, which is a real thing that's described through other academia. It's numerous. It's a system of numerous diverse interconnected agents that adapt, self-organize, and display emergence through nonlinear interactions and feedback loops. So what we need to do in our modeling effort is model down all the way to first principles variation so that we can explain behavior, not just predict a specific outcome. And we use those models to reveal leverage points in the system. If you take the old approach of just thinking about a more mathematical point of view on what we do for advanced analytics in healthcare, you'll be thinking about what can I predict? What sort of algorithms can I do? How elegant is my math? And so you'll pursue things like predicting case length, predicting cancellations and no-shows, likelihood of admit or surge prediction in the ED environment, maybe demand prediction in the transfer center, or census in the hospital, or discharge disposition. As opposed to when we're really driving the institution's ability to see, anticipate, and act on the levers that matter most. So trying to get closer to that better definition. When this is what we're trying to accomplish, the connections here matter. So we'll probably be pursuing instead something like likelihood of PACU boarding for the purpose of adjusting the schedule upstream, likelihood of ED boarding for the purpose of having an impact on staffing. We may still predict census for the purpose of informing diversion policy or focusing discharge effort. We may predict census at the unit level in order to make some impact or change to schedules upstream or direct activity within the hospital, like cleaning priority. So we are moving beyond prediction, where we're just looking for a forecast of an individual outcome, to this system modeling perspective, okay? So we're gonna look at an example that we went through in the overall, and now we're gonna talk about simulating with it. Or we went through in our previous conversation about overall modeling. And now we're gonna do some more direct look at what it would look like to simulate this. So this is the PACU and patients transition from the OR into the PACU and how that sort of ripples through the system. If you were to take that traditional prediction approach, the instinct would be, yeah, I think I could predict when the PACU, let's say, is going to reach capacity or when it will be overflowing. You would be trying to produce some result like this to say, on January 1st at 1 o'clock, we predict the census to be 15. At 2 o'clock, it'll be 19, and at 3 o'clock, it'll be 25. That's your breaking point. And so that's what we would have. And you would have to trust our accuracy and ability to do this. We might even be able to do it somewhat effectively. And you get an analyst that's very excited about the result, and it is exciting, at least you know the math part of it. But if you follow a project like this far enough, you're going to run into a meeting that looks like this, where the administration side is saying, well, hold on, that is really neat math, but it's not actually helping us. The data side may say, well, that's what you asked us to do. Admin side will say, well, you can't trust us to know what we need. And the data side will get defensive after that. I've been in too many meetings that are like this. So why does that meeting happen as opposed to something presumably like what's on the screen there that looks a little more collaborative, where a high quality model can predict PACU occupancy by hour? That is the only thing it can do. And it's stuck to whatever accuracy it's able to produce each day. It doesn't help us look at the next level of question, the next thing that's needed to have a practical effect on the system. Things like how quickly do OR rooms back up when the PACU is full? How many cases will be delayed? How long a recovery bottleneck will last? These are things that you could actually make decisions on. You can go and create action with understanding like this, as opposed to at 2 o'clock you'll be at capacity, which is that previous approach. So we're still going to use the framework we talked about before in starting by defining units, mapping the flow, adding constraints, characterizing variation with distributions, and we're at the final step where we simulate scenarios to measure probabilistic endpoints. So we start with that defining of units and figure out what matters. In the case I'm putting in front of you, it's our PACU. We want to get to realistic constraints so that we are infusing some reality into this modeling of the system, and we want to characterize that all with distributions so that we have a more realistic point of view on what the future could look like. After that, we're trying to turn it into outputs, things different than you might be thinking, or different than surely the example we saw before, where we're just saying our prediction for this point in time is that the census will be 25, as opposed to we've simulated many times over, and here are the many results we have so that we can add a more probabilistic statement to that to say the likelihood of hitting 25, a census above 25 is this. So we can better understand the system instead of just having the prediction that doesn't let us look into any other questions. So let's just start with this kind of simple level of simulation question that we're going to solve for. How do small variations in surgical or recovery times change whether the PACU hits capacity on a given day? And so this is going to help us look at sort of real system behavior, how the OR and PACU flow. And what we're going to do is we're going to fix some operational constraints in here. And this is all happening in code that I'll share with you. I'll do another video to walk you through the code and exactly how we're accomplishing this. But I want you to start with the intuition. From there, we move on to the questions like a probability of congestion under certain constraints. How often will normal variation with a specific schedule push the PACU over its capacity? So remember, this is the step we are at. So we start by defining the units. Actually, with a question like what we are now looking at, we probably primarily care about our OR and PACU and maybe a little bit about the downstream hospital. I've got the following constraints sort of encoded into this example that you'll see through code, that we on the hard constraint side are saying this PACU has a finite number of bays. We've just got a capacity for 3 patients, that there are urgent and scheduled cases, and the urgent cases must run regardless of the load. The case durations of the PACU are going to vary. We're going to let that go with historical distribution. And the arrival patterns for our urgent cases will be uncertain. Some of our softer constraints is that we'll have a preference to avoid late day OR bumps and a desire to minimize cascading delays. So you'll see in the next video in code how we accomplish this, but we start with, can we characterize the variation? And the core variation here is in that length of the stay in the PACU, or actually length of case, in the OR upstream. So we take a look at the data set. We look back at history to understand over time what has the length of stay been for patients that arrive in our PACU. So we go ahead and get that from history so that we have a distribution to sample from when we simulate. So we move on and we simulate. So simulation is where we replay, for an example, the same surgical day under many plausible scenarios. So we keep the schedule fixed, but we vary the elements, primarily that PACU length of stay, so that we infuse some variation of possible combinations of how the cases could go together. Then, to understand how the variation affects that PACU capacity, we select that real surgical day from the data, compute its baseline PACU occupancy of what actually happened, and then repeatedly resample that with different recovery times based on that natural variation we see from the distribution. And we simulate this day over and over again to see, under this case schedule, how often will the PACU exceed capacity. So here's the case day that we pick. We grab the January 9th of 2024. There's 6 total cases here, mix of urgent and elective, only 1 urgent, 5 elective. And we've got our historical capacity out here just to see what really happened in this, to see an occupancy that's bumps above our capacity line of 3 there. But then we move on and we simulate so that we can redo this day many, many times. So in our example day, when we simulate it 200 times, you see there's a very small amount of times that end up with a peak census at 2 or 3. Actually, the majority of our simulations end up with a census or a need for beds in the PACU at 4 to 5. So that result is telling us a schedule like this is very likely to be above our capacity. We also, can start asking different questions like, okay, of these 200 simulations, what was the distribution of how many minutes we spent over capacity? So it shows that there's also some variation in how long this might last, right? It might be very little in that there's 0 time over capacity or less than 10 minutes. But there's absolutely examples from just that normal variation with the same exact caseload that we end up with many, many minutes of the day over that capacity. So this is the power of moving to a simulation, is now we have 200 example days and we can start asking questions about what happened on those days where we held the cases steady and we just let normal variation apply to the cases of the day, so we can see likelihood of different outcomes. So that's what I want you to see. Next, you'll go look at actual code with me, so you'll get a more direct sense of how we'll do this in Python. And you've got a script to run against the data set that I've given you. So you're all set to actually do this and to take it and tweak it and continue to work with it. So I hope, though, at this first level, you're just seeing the core principles come out, that we are looking for system components. We are trying to figure out what are the units that matter and how do they relate. Then we are looking at distributions, not single point estimates of what's going to happen. And finally, the output we are pursuing here is not a single answer. It is probabilistic. It's what is the likelihood of different events, different scenarios, to understand more deeply. So some of the key takeaways: that structured framework helps us do this with some repeatability and clarity, that we are absolutely pointing to modeling distributions, not just predictions, looking for those probabilistic endpoints. And there's a real opportunity to apply this to tons and tons of scenarios throughout healthcare analytics. So thanks for sticking with me. We are moving on. Next, we'll look at code for simulation. Then we're going to head on to another tactic, optimization, kind of a next level of this in making a decision with simulations.